We can start now. Good afternoon, everyone, and thank you for joining today. So this is one of our monthly webinars, and we are the Circular Economy Powered Renewable Energy Center. And basically, what we are about is how do we promote the principle of circular economy in renewable energy transition across Africa. Today, we are privileged to have Dr. Vijay Packer to present to us on the title From Modeling to Megawatts, Making Microgrids Work in African Communities. And Dr. Packer is a senior lecturer in electrical power systems and smart grids, and he is within the School of Engineering, Infrastructure, and Sustainability at the Montfort University. And his research is in the area of smart grids, specifically on the topics of distributed resource integration, microgrid operation and control, voltage regulation, and distribution system modeling. So today we'll be hearing quite a lot, but he'll be focusing on our work at CEPREC, which especially the work in Work Package 4. So please welcome Dr. Packer, and thank you once again for joining. Over to you, Vijay.
Thanks, Moiva. Thanks for the nice introduction. It's an honor to be here. Thanks for inviting me and to ask me to talk about microgrids and specifically about this topic, which is a very interesting one and focusing on the CEPREC project particularly. So the topic of this today's webinar is about modeling of microgrids in specific and how that is works in relation with the project that we are doing, especially in the countries that we are partnering with. So microgrids are now the mainstream solution for, as you know, for rural and peri-urban electrification in Sub-Saharan African region. That is where we are focusing on. So different players like governments, donors, private developers have adopted microgrids or mini grids as a fast and flexible alternative to grid extension, especially in these regions. Our experience from the field shows that the microgrids begin to face operational challenges only after a few years of commissioning. These challenges are rarely caused by lack of installed generation capacity, whether it is PV generation systems or small hydroelectric turbines or small wind turbines, etc. But they mostly arise because systems are designed using simplified feasibility models. I'll explain that with few examples as we move along. And that these models not necessarily do not represent how microgrids operate in their full functionalities over time. Therefore, this webinar focuses on closing that gap, drawing on the PhD research, which again I will highlight towards the end of the webinar on this program, and work on other aspects of the project. And it shows how incorporating electrical network behavior, evolving demand, and user interactions leads to microgrids, which are more reliable and more effective as real communities grow and change in these regions. So this is a nice picture. You might find these kind of pictures online, especially installations in Sub-Saharan African regions from private players, NGOs, and governmental organizations. This is the one I put from Abuja, Nigeria, because I had been to Abuja in a previous workshop in September last year. I really loved that place. This is an example of what we would like to call it as a mini grid or microgrid. Again, the definition would differ. But if you want to stick with a specific definition of microgrid, there are 2 or 3 definitions. One of them is from IET, which is a professional organization in UK, which says that microgrid is a local integrated energy system which comprises of interconnected loads and distributed energy resources. It doesn't specify as to what kind of loads or what kind of distributed energy resources are, but it leaves open for interpretation that these would be the ones that is specific to that context that we are talking about. For example, in this case, it could be solar PV panels and households as domestic consumers. And these systems should be capable of operating in parallel with the main grid or independently in an intentional island mode. And again, coming back to the concept of mini grid and microgrid, there are some distinctions. Mini grids typically are slightly larger in size and can serve entire communities or regions. They're often designed to operate independently in remote areas, but they can also connect to the main grid. Can also integrate multiple energy resources, solar, wind, even fossil fuels. Microgrids, on the other hand, are usually slightly smaller, designed for specific applications like single facilities or campuses. And there are various examples. If you look at organizations such as Renewable Energy Agency in Nigeria, where they have microgrid installed outside of university campuses and so on. Microgrids have capacity to interact with main grid, so there is again commonality with the mini grid, and they're commonly used in even military bases, hospitals, or industrial facilities, mainly to enhance the resilience and enhance the reliability of the energy supply. Coming back to the operational reality of microgrids within this region, they're mostly made up of low voltage, mostly radial distribution lines, that is one single power supply to the consumer, one path of electrical power supply, and dispersed residential, commercial, and productive use loads, and less of big scale industrial loads. These systems are mainly characterized by long feeders, high resistance to reactance ratios, and limited upstream grid support. So therefore, voltage drop becomes strongly dependent on active power flows, and as demand increases, that I mean by demand would be the electrical demand, the current increases and voltage drops rise almost linearly along the feeder. So in many cases, customers at the end of the feeder experience undervoltage even when there is sufficient amount of generation capacity. So in dense grids, feeders are shorter, transformer are more closely spaced, and upstream grid provides strong voltage support. That intuition does not carry over to rural sub-Saharan African microgrids, where voltage limits are often the first operational constraint that is encountered. So again, this is one of the graphics that I got from IEA, International Energy Agency. They have a nice report on specifically focused on the African context. And in that, what they're showing here is not just more renewables, but a structural shift in where and how electricity is produced. So in most of SSA region, electricity growth is not dominated by large transmission connected power stations, but mostly it's increasingly comes from distributed solar, PV panels, mini grids, and local generation that are close to the demand. So the distance has matters in this case. This has a direct implication with microgrids. So firstly, low voltage networks become the main arena of operation, not a passive afterthought. Second, variability is no longer averaged out by the transmission system. And this is felt locally at the feeder level and even at the household consumer level. Also, it misses this kind of planning around annual energy balances, etc., misses operational bottlenecks like voltage rise, thermal overloads, and phase imbalance, etc. So this is exactly why traditional feasibility studies are not sufficient, and we need to go much beyond. Can the network actually operate reliably over time? That's the question that we are trying to answer. This is again one of the graphics I really liked, which again gives an idea of geographically how these systems are spaced and what kind of systems we are talking about and how distance matters. So all of this feeds into the issue of capital investment. How much needs to go into distribution networks, system flexibility, storage, integration of infrastructure, etc. And the key insight from microgrids is that if microgrid suffers from frequent voltage violations or fails to meet demand when demand grows, or if the microgrid has to repeatedly fall back to diesel generation, etc., then it becomes financially risky to even proceed with the project. Um, so on the one hand, you have feasibility studies, which could make the project feasible on initial set of studies. But when you go deeper into much more technical analysis, such kind of projects might not be financially feasible. So this is where network-aware, behavior-informed microgrid design. It does not necessarily mean that we are trying to over-model the microgrids, but it is a type of risk mitigation that we are trying to do. So we are trying to explicitly model LV network constraints, that is low voltage network constraints, bottlenecks, and also we account for demand evolution over time, whether it is demand type of demand growth within the existing microgrid, or if the demand increases geographically. And also crucially, from CEPREC's point of view, we are treating the storage as an operational asset rather than just a backup capacity. And there are plenty of examples from different parts of the world where this has been the case. But in case of CEPREC, it's slightly unique because we are focusing more on second-hand EV electric batteries. And we are trying to incorporate that within the modeling framework. So this just like to talk a few minutes on the limits of conventional microgrid modeling and how we are trying to overcome this. So many such kind of modeling microgrid planning tools assume copper plate network, that is where all generation or loads are effectively connected at a single node or a single bus bar. Without the detailed network diagram of the grid. There is recent work that has been going on to update this kind of a modeling framework. But most of the literature out there or the modeling framework talks about this kind of feasibility modeling, where while this is acceptable at initial stages, feasibility screening, it mainly hides the physical mechanisms and structures that govern how the microgrids operate in the real world on the ground. So things like I mentioned previously, voltage drop, congestion, bottlenecks, imbalance of phases, um, and different kinds of loads, types of loads specific to the Sub-Saharan African region. These are inherently spatial phenomena that depend on where the loads are connected and what types of loads are connected and how the currents and powers flow in the network. So in addition to demand, demand is often treated as a fixed point without going into the physical location aspect of the demand. Also, demand revolves in response to service quality and other socio-economic factors, and that is one of the highlights or uniqueness of CEPREC project, with different work packages working on different aspects of this whole system integration, whether it is the social aspect or the economic aspect or aspects related to integration to the main grid. Therefore, what traditionally happens in such situations is that the system planners or microgrid planners significantly underestimate the future stress on this kind of distribution networks. This is one of the examples of an MSc student that I had a couple of years ago. Excellent work. Just to give you an idea of how the Homer system works, wherein the feasibility analysis is done, techno-economic feasibility analysis is done. So this is an island in the western part of Sierra Leone, and this had a history of iron ore mining and the village, and it closed down quite early. So there's estimate of few thousand of people. So if the student did GIS mapping and got some network data, but was not able to do that in the feasibility study. So he had to start with the Homer software, wherein different scenarios were considered. whether it is a case of hybrid solar plus diesel generator, which is most of the cases of microgrids in these regions, or with a battery, or with the pumped hydro storage. So different scenarios can be designed and evaluated using these kind of feasibility studies. So the configuration gives out different focuses on different indices or parameters to analyze whether any project is feasible or the microgrid is feasible. And one of the most common functionalities, the parameters looked at is LCOE, which is least cost of energy. So by the looks of this Homer model, the case 3, which is that of a hybrid solar PV panel plus diesel generator plus pumped hydro storage, is the most effective one. Of course, we have to keep an eye on the other other functionalities as well. But this doesn't take into account the various dynamics that I mentioned previously, whether it is the aspect of evolution of demand through multiple years, or the locational aspect of the demand and the network constraints, or even if you look at the aspect of the behavioral aspects of the consumers and how they respond to the changing generation scenario, and so on. So there are limitations which we are trying to focus on the project. So feasibility studies typically ask whether installed PV, diesel generators, and battery can meet this expected energy demand. And generally, these studies often conclude positively. That's generally the conclusion from most of these studies. Our reliability is not determined by energy balance alone. So its reliability is a local property with respect to each customer, and whether the customer is receiving power at an acceptable voltage level and frequency, and at that specific location on the network. And even if you go beyond acceptable voltage and frequency, what is the quality of the power that they're receiving and how reliable it is, etc. So as demand grows, whether within the microgrid or it grows spatially outwards, outside the microgrid, becomes more unevenly distributed. So some of the sections of this network could become overloaded, or it can experience excessive voltage drop. And also, depending on the customer behavior, how they engage with the electricity, this issue could be aggravated. So again, this could lead to customer complaints, damage to the equipment throughout the system, from the point of contact to the main grid to the customer, and even disconnection. So even though the system might appear on paper energy adequate at an aggregate or a top level, we have to make a distinction between energy adequacy and service quality. And this seems to be the recurring theme in the research in this field, especially distribution level, low voltage level distribution systems. And it's particularly relevant to microgrids and mini grids, and even more so particularly relevant to the Sub-Saharan African region due to the nature of the loads and the sparseness of these networks. So the philosophy of CEPREC, or the approach, is to recognize that microgrids are socio-technical systems, or if you want to call it a socio-economic and technical systems. Electrical constraints, human behavior, um, uh, uh, trading or interactions between customers, or between the customer and the energy supplier, and operational decisions, these interact continuously. So this work package, number 4, focuses on linking all of these layers. If you consider each of these factors as one of the layer, rather than analyzing them in isolation, which is traditionally what has been done till now. So the objective is not to produce more complex models, just for the sake of covering all the aspects, functionality aspects of the microgrid, but it's more to produce models that remain valid as the system evolves. So scalability comes into picture, and these models should be able to inform operational and planning decisions. So in a way, it's a more a living organism rather than fixed approach that we take in other feasibility studies. So this is one of the examples for the kind of load profiles that we are looking at. I do not want to go into the details of how we are collecting this data, what modeling we would do, etc., because that's a big subject area on its own. But in essence, we would need this kind of a data for residential customers or small enterprises within the community, and either collected through surveys or through metering data or through historical data, etc. And these would effectively feed into the modeling framework. So we consider the time aspect and the time step aspect as well. And of course, the behavioral aspect of the customers would feed into these demand profiles, which would be more dynamic and more evolving as the scale of the microgrid increases or evolves. Another aspect of modeling is the control of the microgrid, wherein there are different aspects to the control of microgrid. Again, there's plenty of literature on these aspects, divided into different levels. One is the immediate, very primary level control mechanism, which is more about voltage and frequency control and reactive power control, etc. But we would be focusing more at the level 2 control, which we call it as a secondary control, or sometimes the tertiary control as well, which will look at the optimal dispatch of generation sources, any dispatchable generation that is there, and how best we can make use of battery systems, battery plus renewable systems, to meet the demand, and how this evolves as the demand is evolving, how these functions can be adapted to that. Of course, there are higher level functions which would talk about interactions with the distribution system operator level, which we usually call, that's the name we give for the network operator, low level distribution network operator in UK. And they would also be sometimes in different markets, they would be involved in acquiring the energy from the generators and managing the grid connections with the microgrid, etc. So we are in the project. We are trying to bring on board network operators in different regions, and discuss with them what the issues are from their point of view, and how a modeling approach could bring those phenomena into the modeling framework. Again, a few examples from literature about what a microgrid generally looks like worldwide, and what the objectives of or different microgrids are. So the connection with the microgrid, with the existing distribution system, or would it operate in the islanded mode? So the objective of in such a scenario, the objective of output shift control is to shift power generated by, for example, PV and wind turbines using storage batteries, and thereby to make effective use of renewable energy resources, and thereby realize reductions in fuel consumption. So through effective operation of diesel generators, and this sometimes is more relevant in the regions that we are talking about, where there is a lot of propensity, a lot of interest in using or keeping this diesel generators operating. So specifically in such scenarios, control is carried out over charging of storage batteries with PV generated power, or wind turbine if you have that, and then discharging to suppress peak demand levels. So for example, in small remote islands, because demand peak is during the evening for lighting, and demand is very less during the daytime, when there is generally the PV output is more. So surplus power may be generated during the daytime. So it is used to store the charge in storage batteries, and output at grid connected point is maintained at zero. So therefore, during peak demand times, the output, if the diesel generator is intended to be operated, the output from diesel generators is controlled so as to not to exceed a set value, while requirements over the set value are supplied from storage batteries. So this kind of modeling, wherein we are, rather than completely eliminating the diesel generators, we are trying to make effective use of those in as many situations as possible. Of course, that is in islanded mode of operation. But in case of other urban microgrid situations, there could be a strong connection to the main power grid, wherein we have a microgrid central controller, which is dispatching most of these generation sources. And there could be opportunities for customers to actively engage with demand response, or they could act as prosumers, that is, they are producers of electricity and consumers as well. That we have seen in multiple cases in microgrids, which so rooftop PV panels, or for example, in UK we have mini CHP units in houses, or battery packs in garages, etc. So to begin with, within this work package, what we are trying to do is we are trying to start with the benchmark model for a low voltage network. This will serve good purpose because of the nature of the distribution network that we would work with would be quite wide in variety, in the sense there could be three-phase low voltage networks, two-phase single-phase voltage network, and we could be modeling overhead distribution lines or underground cables and different kinds of components, different kinds of connections for transformers, etc. So the benchmark networks do give us the opportunity to do that kind of modeling. And then we do take into account all kinds of renewable and non-renewable generation sources. We generally categorize these as distributed energy resources, whether it is a fuel cell or a small wind turbine, photovoltaics, um, or it is flywheel storage, batteries, and etc. So the idea is to model the microgrids, and make it electrically as rich as possible. And this would form one of the layers that I spoke about earlier. And then also modeling of the battery itself and the use of battery in optimally discharging or optimally dispatching different generation sources and matching the demand, etc. So these would happen, would be looked at different time frames, not just within a day, but the planning also would need to happen for weeks and months in advance. And the battery could be used for different purposes: reserve capacity, coordination with the energy sources, and with demand response, or for arbitrage. So, for example, battery could supply about 25 amps for about 1.5 hours before the voltage would drop to about 10.5 volts, and so on. So I will probably go through this part quite quickly, because it talks about more technical modeling of the battery themselves, and we are working with other work packages on this aspect. So there are mainly two challenges with battery problem. The battery model. The first problem is to get a model that is not too complex, but accurate enough. And the second problem is to get the parameters from manufacturers or own measurements needed for the model. So there are experts on other work packages working on this, and in collaboration with them, we are trying to bring these models onto the electrical model of the microgrid. So only a model with good appropriate parameters can deliver good results. So we are looking at characterization by the capacity of the battery, internal impedance, open circuit voltage, self-discharge, and so on. So what are the framework components that we are talking about? Mainly, as I said, we are looking at the participants, the players, whether it's a distributed generator or owner of these generators, consumers, or any entities such as aggregators in different scenarios, or market operators, or it could be a microgrid operator itself. And we are looking at all the physical assets themselves. Um, and of course, the main thing is how do we interlink all of these through the processes of exchange of information, which is necessary for optimal dispatch or microgrid control, and what are the market mechanisms that we can deploy for each of the different contexts that we are looking at. Different regions would have their own market rules and regulations, and regulatory authority would have an oversight of them. So what are the trading rules that would allow us to model different scenarios and different within this framework? Um, so another aspect for this modeling is modeling the behavior of the consumer, and also the behavior of the entities themselves. Entities in the sense energy supply companies or network operator, etc. Most of the times, these behaviors can be captured through their restricted operations, for example, especially with regard to network operator. But sometimes it's very important to capture the behavior of the customer, which would go into what we call as agent-based modeling. And this in turn will allow us to assess different scenarios in the future across different timescales. How techno-economically is the whole system viable? So this is where the deep distinction between this kind of modeling framework and the earlier stage of feasibility studies that I showed, and how rich the system is with multiple layers. And then in the real world, this could be used to address many significant issues. One of them, just to highlight those for lack of time, is the issue of interconnection of these mini grids. And as I earlier showed in the first earlier part of the presentation, first few slides on how the distance matters between the micro mini grid and the point of connection and the main grid, and how all of the mini grids could come together to act as a big system. So it has real world implications, and the modeling framework that we are developing will definitely help for that. So I'll just highlight a couple of doctoral research themes that we are looking at the university at DMU under my supervision. One is agent-based modeling of different players and assets and processes themselves, and the issue of scalability within microgrids and across microgrids. So each of these projects addresses a different dimension of that problem, but they're all tightly linked with each other. And not to forget, across all of these strands, second life electric vehicle batteries are investigated as a key flexibility resource. So just to again highlight these different themes, modeling of multiple players and the assets capturing the behavior and operational interactions, scalability within microgrids, how demand evolves over time, and how network storage and control strategies must evolve, and across microgrids or mini grids, assessing how, when, and how interconnecting mini grids or connecting to the main grid becomes technically and economically optimal and feasible and optimal. So all in all, to conclude, I would like to put that as my last statement sentence, as if we design microgrids to evolve technically, economically, and socially, using the tools that I mentioned earlier, we can move forward from electrification projects to energy systems that last. And that is one of the real highlights of the CEPREC project. Sorry if I've gone overboard. Thank you for listening to me. And these are my contact details if you want to contact me outside of this webinar. But I think I'll open up for questions if you have any. Thank you.
Thank you very much, Vijay. Thanks, very insightful.
No problem.
Yeah, any questions? If you raise your hands, I will allow you to speak. Any questions, comments?
Now, by the time you get questions, I just wanted to highlight one thing that I haven't presented, is that there's a strong interaction with other work packages, especially with regard to the social aspect, the economic aspect, etc. So hopefully, in the coming months and next year, please watch out this space for some more results from those interactions.
Thank you. So I see Udochukwu, but please can you unmute yourself and ask a question?
Yes, thanks, Prof, and thanks, PJ, for your presentation. Yes, I just want to know from the point of view of having multiple grids connected, forming the system, like you have perhaps looked at it in your presentation. In that case, when we look at deploying of second life components, EV components into such a system, how are we able to gauge the reliability of those components? Is it going to increase in such a case? Is that what you are predicting with your agent-based approach? I want to believe maybe that is what you are predicting, or otherwise, if you have them as a standalone system, is there a lower reliability, or what are the trade-offs? That is one question. The other question is with regards to the different sources that you are currently allowing on the grid. How does this translate to the feasibility of the different CEPREC partners that are involved and the potentials that they have in their different geography in terms of what they are able to generate with? Because I see you did mention that you are flexible with the different sources. You are looking at it from all angles, but are we eventually going to be constrained by the geography where the project is being coordinated here in Africa? Those are my questions. So thank you.
Yeah. Thank you. So if I may answer the second one first, the models that we start out with, even though they're benchmark models, that's the reason for being them the benchmark models, is it is able to accommodate all kinds of resources and all kinds of components, non-generating components as well, and all kinds of customers as well. But there is a limitation to it in the sense of the network topology itself. So that is where the bespokeness of the individuality of the system would come up. For example, if you look at one particular region, which might be having a more radial kind of a network, and maybe underground cables, etc., then suddenly if you move on to focus your study on a different region, which is much more peri-urban, for example, and much more diverse customers, the network itself would be, topology itself will change. So the modeling has to change in the sense that the network layer would have to change. But the framework necessarily would not change, because though the network might change, the agent-based model, which captures the interaction between different assets, would still remain the same, because it will be able to, it should be able to capture the variety of these customers or the variability in these kind of generation sources, etc. Similarly, from the market, the economic point of view, if you strictly do only the economic modeling, you're designing, you're focusing on the modeling of a specific kind of market structure, which is very difficult to adapt to another market structure or trading mechanism, etc. This is where agent-based modeling could be helpful, where it can be quickly adapted to different context. So the answer is broadly yes. We can adapt, and that is one of the main objectives towards the end, one of the deliverables towards the end of the work package, wherein each of these frameworks should be able to address different regions. But it would also be generic in the sense when we are coming up with some innovative trading mechanism or some innovative dispatch strategy for all the generation sources, that algorithm or that strategy would be equally applicable for different contexts. But of course, if the social context is different, then for example, if there is no possibility of peer-to-peer trading happening in one region, then of course we are not able to model that. But that feature would be switched off in that way. So it is a task to generate different reports or different models for context, but there will be a generic skeletal framework which we can hand it over to one particular partner or a group, and they can make it specific to their region, and we can work with them. With respect to the first question, if I'm correct, I think you asked about use of second life electric vehicle batteries and whether would this increase the reliability and how would we do this. That largely depends on the kind of model that we have for the second life batteries and the parameters that we are focusing. For example, state of charge, capacity, etc., and for what functions we are going to use it for. So that we have to work, and we are trying to work closely with other work packages. And once that modeling framework for the battery is finalized, depending either from measurements on the ground of the batteries or the theoretical models, then we should be able to analyze whether the system is reliable or not. And we of course use different indices for analyzing this kind of reliability depending on what question you're asking. For example, if you're say looking at reliable number of hours that the customer is served electricity with, or the quality of power that the customer is supplied electricity with, based on these second-hand batteries, then there are systems in place which we can use to model and answer those questions for those indices. But for now, of course, I can't answer whether using it within the grid at a particular location in a particular way, that be better or not. That's actually the question we are trying to answer as part of CEPREC in a way. Is that correct if I understood your first question right?
Yes, thanks, Vijay. You answered correctly. I just also wanted to check with you. Do you already have a size of the mini grid that you will be modeling? There like some case studies already you've done to predict the size of the mini grid that we are looking at? Or is this also something you are developing?
Yes, definitely. I think that's a really good question. We are looking at it from 2 points. One is the models that are there in the literature already, whether standard models or benchmark models, and as closely related to the SSA region as possible, because most of these benchmark models are led from a European point of view, from that context. So we have to, in a way, my hope at the end of the CEPREC project is to come up with benchmark models for the SSA region, for each region. So each region would have its own models. Or we are also signing up MOUs with different organizations to get us the on the ground network data, which we are quickly going to take it. But we have to be careful with that aspect as well, because there is a chance for us to be much more focused rather than trying to be a bit more generic of different contexts and different regions, etc. So we have to be careful in what kind of models we start with. But of course, the quick answer is we have electrical models. We can quickly deploy that in software packages. And some of my students have actually gone on to the ground and collected data from regions, whether it's the Sierra Leone case or one student in Kenya etc. And we can quickly design that microgrid on the system. But the idea is once we have a sample network and the results from that, we can share it to different partners of different work packages. And once they get the sense of what are the limitations of designing the microgrid and what are the issues, then we can work in collaboration with the partners and to address any social constraints or economic constraints and so on.
Thank you, Vijay. Any other questions? Please feel free to raise your hands and I will.
Moiwa, we have a comment in the chat.
Okay.
Um,
Karen.
Sorry. So it's from Jose, and he wants to. He firstly congratulates the team on the work. And he just writes, it may be an impression, but since most microgrids are funded by governments, they seem to try to limit them. I visited some cases in Ghana where the houses have their load limited by the energy meter in terms of how much energy they can use during the day and maximum power limit to avoid load side expansions. My point is that most of the problems seem to be related to budget availability, not to technology. Given your greater experience in the African context, do you share the same perception?
Thank you. That's a wonderful question, actually. That actually one of our PhD student is installing microgrids, and this is exactly one of the issues he mentioned. I think in Nigeria. So we know about the reality, and this is exactly why I'm a bit careful about claiming that any modeling framework that we come up with is going to be applicable for all the contexts. It has to be context specific, and also it has to be on what question we are trying to ask and address. If the question is about the economics of it, and similar to the homework package that I showed, what is the least cost and what is the capital outlay, and over 5 years, 10 years, how do we go about looking at financially, then that's a different question, and the technical feature will be taken into account. But if you are trying to answer a technically specific question as to look at if there is any constraints on the network, or if there is issues with power sharing, and can there be a market that can evolve within this microgrid, and this load limiting is hampering that, we can create that scenario, and we can model it and then analyze it, and then come up with a report which would strongly highlight this aspect and probably show a different market pathway for the installer. And that is where we also need to engage with government officials, and CEPREC is really of all the projects that I have worked so far, CEPREC has been really good at engaging government officials and trying to engage with us and look at us as partners who can ask and answer these kind of questions and then inform policy in turn. But yes, we do take that into account. And if I'm right, one of my Kenyan students said, talked about the meters and how they are actually charged, and there is issues about that. So every day I get to know about this context, and that is where the feedback from partners, and when we towards the end of the project, when we work with um, context specific models, we will be taking all of this into account as part of the larger report. But definitely thanks for highlighting that.
Thank you, Vijay and Nasi. Any other questions or comments or additions? Yes, there's a new message. Okay. So this will be available on YouTube. The recording. I guess the slides still will be made available most likely on our website. I'll check. But definitely the recording will be available on YouTube to answer William. I guess any other question? If not, once again, thank you for joining the webinar, and many thanks to Vijay for presenting. Very insightful. We have this every month. So please, you can follow us on LinkedIn or any of our social media channels, and you get up-to-date information about our events and activities. Once again, thank you for joining, and enjoy the rest of your afternoon.